growth, and I ran across this little graphic, which is kind of interesting. National Forest land management, the timberland component on national forests. So the vertical axis, millions of cubic feet of wood, and then year on the horizontal axis, from 79 to 2010. And you can see on here gross growth and net growth. Right? Those are two of the definitions that we made for growth. And I'd say this is a pretty disturbing trend. Harvest is, I mean, there's a little bit of up and down now, but it's gone down significantly since the mid to late 80s. And corresponding to that, huge increase in mortality. So of course it depends on what you're managing your forests for, but if I was going to manage those forests for timber, I wouldn't be putting myself in that situation. Of course we manage a national forest for all sorts of benefits, right? So maybe they're producing good raccoon habitat. So you'll see these, right? That's the first thing you need to ask. What growth are you talking about? What definition of growth? And if it's from a forester, you'll get a specific definition. Okay, so we talked about trends, factors, so forth for tree and stand growth. Now we want to start talking about predicting stand growth. How do we go about predicting what the future might look like? We'll talk about two techniques in general, direct projection techniques. And by direct projection techniques, I mean techniques that involve actually observing growth in the stand you're interested in. Direct observation of growth in the stand you're interested in, and then applying those observations of growth to peer into the future. There are lots of such techniques. We'll only look at one, the one we look at today. This will be the only time we talk about direct projection techniques, and that technique is called stand table projection. The other main category, indirect projection techniques, and these are really the growth and yield models that I've alluded to in the past. So there, we're not necessarily observing growth in the stand whose attributes we want to project. Instead, we rely on models that have synthesized growth data from a broad range of stand conditions. And then we're using those models for our particular stand. And of course, where do they get data for these indirect projection technique models? Permanent sample plots, right? That's one of the uses of permanent sample plot data to calibrate these growth and yield models. Of course, we want to make sure, as is the case with any model, that the stand we're dealing with is within the range of conditions that are represented by these data that were used to develop the model. So we want to make sure that it's a rich data set that was used to develop any model that we're going to apply. So direct projection techniques, one example, stand table projection we'll talk about today. And we'll spend the rest of the semester talking about these examples of indirect projection techniques, these growth and yield models. Okay, so stand table projection. Well, today, growth and yield models are really where it's at. So you might ask, why would we cover a direct projection technique like stand table projection? Well, there are several reasons. One is it has historical significance. This used to be very, very common way that foresters use to peer into the future. There's still a lot of cases where this is the technique, consulting foresters, for example, working with small woodlands or wood lots in particular, where probably the growth and yield models that are available don't have data from woodlots, right? Typically, particularly ones that have been grazed by cattle and so forth and so on. So it might be important to use growth data from that stand project into the future. And if there's no model available, you need to go with something, and this is an option. The other reason is it really does a good job of introducing two categories of growth and yield models that we'll be talking about starting next week. Individual tree growth and yield models and diameter distribution growth and yield models. So you'll see some real analogies between what we talk about today with stand table projection and those two categories of indirect projection techniques. So what's this technique all about? Well, basically we're going to assess the current status of the stand and project it ahead. And what we're going to project ahead is the DVH distribution. So we're looking at the horizontal structure of the stand. Typical time intervals for this technique, quite short. And you'll see why. 5, maybe 10 years, maybe up to 15. Get a little bit iffy. We can try to go beyond 10, really. So short-term projections. And what we're projecting is the DVH distribution. So we're going to start with an assessment of the status of the stand, characterize its DVH distribution, and then project that DVH distribution ahead through time, using growth data collected from that stand. So inputs, what do we start out with? Well, if we're going to project a stand table, we need to start with a stand table. What's a stand table again? Trees per acre by species and DVH. Exactly. So that's how we're going to establish, here's what the stand looks like now. Then we also need to have increment data, and since we're projecting the stand table, the attribute we need to project is DVH. So we need DVH increment data. Where are we going to get that? How are we going to get that?
Measuring it.
Yeah, increment cores. Taking increment cores. We also need mortality estimates and ingrowth estimates. Well, what are we really talking about here? We're talking about 3 of the 4 components of growth, right? Survivor growth, mortality, ingrowth. If there's outgrowth or cut, we obviously can add that in as well, but we have strict control over that. That's not something we need to estimate or predict. And then finally, if we want more than that stand table, in particular if we want a stock table, and usually we'll want a stock table, which is volume by species and DVH, we'll need some way to go from the stand table to the stock table, which means we'll need some sort of individual tree volume equation. What type of volume equation are we going to need, at least at first cut, does it seem like? Well, what information are we going to have about trees? Species and DVH. So what volume equation type?
Standard?
Not standard.
Local?
Local. Right? Standard requires height. We have no height. Right? Just DVH. So we need something like a local volume equation. So almost all forest inventory packages where we analyze data from a cruise or a timber inventory are going to spit out things like this. Stand tables and stock tables. Very common summaries of any forest inventory. So here we see stand and also stock tables, but stand table where we have DVH in 2-inch classes and a number of species. Looks like probably a northern hardwood stand and probably in Wisconsin, given where this is from. But what's the problem with that stand table that's going to make it pretty useless, really, for doing a stand table projection? And you have to maybe infer a little bit more than what I've told you. But suppose there might be trees smaller than 8 inches in that stand? Maybe not, right? But very likely there are. But of course, when they did the inventory, all they were interested in maybe was current standing volume of maybe sawtimber sized trees. So that's all they measured. Inadequate for a stand table projection. We need trees down to and including small sizes because we want to project into the future, right? And those small trees hopefully are going to become, some of them at least, become bigger. So we need to have a more complete stand table than oftentimes is available to us. So that's the stand table. Second input was this DBH increment. We're going to get it by taking increment cores. And typically we'll take those increment cores by subsampling trees on our line plot crews. Right? We do a line plot cruise, whether with fixed or variable radius plots. That's going to give us that stand table information and current stock table if we want it. We're not going to core all the trees, obviously. We're going to core a subset of trees. And we want to make sure that we get a range of tree sizes in our sample of cored trees and at least all the important tree species are represented in our core samples. The other point that sometimes can cause problem, I say here, take a fixed percentage of trees on a plot, not a fixed number of trees. So let's say we're using 1/20th acre fixed radius plots in our line plot crews. We go along, we get to a plot, got a number of trees on that plot. Rather than saying, I'm going to core, let's say, 1 tree on each plot, or 2 trees on each plot, I'm going to core a percentage of the trees on the plot. So maybe 10% of the trees, 5% of the trees. Why is that important? I take a percentage rather than an absolute number.
Consistency.
Yeah. If I take a fixed number, the low density plots are going to be overrepresented, right? Which means our growth data will be biased high, because presumably those trees on less dense plots are growing faster, right? So we want to take a fixed percentage so we get a good even distribution by density in across the stand. Well, of course, with increment cores, we're not observing future growth, we're observing past growth, right? And this is why we typically don't want to do projections longer than 5, maybe 10 years. So we get past growth by taking the current DBH inside bark, IB inside bark, taking the current DBH inside bark, which we can see on our core, right? And subtracting twice the radial increment, that is for the last 5 years or the last 10 years, or whatever growth period length we're interested in. Maybe we're interested in 7 years growth. Fine. Measure the radial increment over the last 7 years, right? And we need to double that to get increment, to get DBH increment. And so our best estimate of past DBH inside bark would be the difference between those two. But of course, when we talk about DBH, and when we're measuring trees on a plot, we don't measure DBH inside bark, we measure DBH outside bark, right? If it's not specified otherwise, we always assume that when someone says DBH, they mean outside bark. So there also is going to have to be some assumption about bark thickness when we do that calculation. Of course, we can observe bark thickness right now, right? You can see it on your core, as you will see in the next slide. But does that mean that that's how thick the bark was 10 years ago? No. So we need to have some assumption about how bark thickness, maybe it's a constant proportion of DBH. Right? We can make an assumption and come up with a way to convert that past inside bark increment to outside bark increment. Then we can apply this directly observe growth in